Hello, everyone. My name is Toshiaki Koike-Akino from Mitsubishi Electric Research Laboratories, MERL, USA. Today, I'd like to talk about quantum machine learning for terahertz imaging. First, I want to talk about the trends of artificial intelligence, AI, including deep learning and emerging quantum machine learning, QML, as a post-deep learning technology. And we apply quantum machine learning for terahertz sensing for the first time of the literature, aiming for non-destructive inspection. After showing some gain of quantum machine learning, we want to conclude the summary. As you know, AI has many algorithms, including SVM as a traditional machine learning technique. Recently, deep learning shows some promising performance. Then quantum machine learning has been proposed as a new AI technique. The classical deep learning has many architectures, including CNN, LSTM, UNet, transformer, implicit layers, and so on. It showed a great success in media signal processing and even surpassed human-level performance for some applications. However, recently, training deep neural network became more energy intensive. Sometimes it requires a lot of GPU powers, which may produce a lot of carbon emissions. And people consider some different computing modality, such as natural computing, including quantum computing. Quantum computing may drive the fourth industrial revolutions. Recently, IBM, Google, Microsoft, many vendors provided a real quantum processor unit, QPU. And also, we can use QPU in cloud services. In addition, we can use many free libraries in Python and so on. In particular, QPU development has been advancing very rapidly in recent years. IBM released more than 100 qubits QPU last November. Then next year, they plan to release more than 1,000 qubits QPU. And some groups showed the quantum supremacy, including superconducting computers and photonic quantum computers. Around 2014, variational principle was introduced for NISQ algorithm. Later, many different machine learning techniques were migrated into quantum computers, including autoencoder, SVM, generative adversarial network, convolutional neural network, and graph neural network. As you know, classical neural network has a good property known as UAP, Universal Approximation Property. The same property were shown to hold for quantum computers based on data re-uploading trick, showing that either many quantum computing layers or quantum bits can approximate nearly arbitrary functions. In addition, quantum computers were shown differentiable. Then we can integrate quantum layers into any classical deep neural network through the stochastic gradient. Quantum neural network is a key driver for 6G applications, which may have advantages that fewer trainable parameters can support exponentially large quantum states in parallel. And parallel ensemble can prevent overfitting and underfitting. Then potentially the computation can be lower power. Interestingly, when I count the number of articles in Google Scholar over the year, we discovered that the quantum machine learning articles has been exponentially increasing, nearly doubling every year, like a Moore's law. And this annual growth is very similar to the deep neural network article. More importantly, the trend is only 6 years behind. Then we used quantum machine learning for Wi-Fi sensing in recent years. And today's talk, we want to use quantum machine learning for terahertz sensing. As you know, terahertz spectrum is located in between IR and microwave. And such an ultra wideband spectrum can achieve fine resolutions. Terahertz wave may penetrate many materials, and it is non-ionizing. Having such characteristic, terahertz wave can be used for non-destructive inspections, such as defect detections in factory automations. We focus on terahertz positioning. In the past, there are many barcode techniques in optical encoders and magnetic encoders. And using terahertz, we can embed such a barcode to identify the location, for example, elevator positions. And we showed such a feasibility in the past. When we use 2D QR code, we may use 2D raster scanning or 1D raster scanning having multiple transceivers, or we can use spatial light modulations. And we developed such a 2D QR codes. If we use 3D multi-layer QR code, we can increase the capacity of positioning information. However, there is a challenge known as shadow effect. If we have multiple layers, the former layers may impact the deeper layers. So we use some deep learning methods to mitigate such a shadow effect. And we showed such a deep learning method is very effective. And in this talk, we use quantum machine learning to improve the classical deep neural network using quantum neural network. Precisely, we use simplified two design ansatz, quantum circuits, which has Pauli Y rotations and control Z gates. In addition, terahertz TDS signal are directly embedded into the quantum states by using amplitude embedding, which can support exponentially large data samples by using a few quantum bits. And we validated our quantum machine learning through experimental measurements. Here we use 3 papers. Each paper has barcode painted on the front and back surface. Let's see the imaging results. Here, this shows the conventional time-gated reflection intensity. It is very blurry. Then when we use classical machine learning known as logistic regression, we can improve the performance, achieving nearly 90% accuracy. When we use modern deep neural network, the accuracy can significantly increase. However, the deeper layer still has some shadow effect. When we use quantum machine learning, we can improve the performance of imaging, especially for the deeper layer, to predict a clearer image. More importantly, quantum machine learning has only 28 variation parameters to train. However, deep neural network used more than 30,000 parameters. Let's conclude the talk. We first showed the recent AI trends and showed the recent advancement of quantum machine learning. We introduced the use of emerging QML for terahertz imaging. We demonstrated the first proof of concept study for future quantum society. Then experimentally shows the feasibility of quantum machine learning assisted terahertz imaging systems. We achieved the state-of-the-art performance with few parameter quantum machine learning, then validated nearly 100% accuracy for 3-layer double-side imaging. Using the hybrid quantum machine learning, achieves a gain over a classical deep neural network. There are still many open problems for future work. If you have questions, please contact me. Thank you so much.